when we're working out the derivative using the product rule, we really go for the similar approach as if we were doing the chain rule. That is, we substitute a variable u in on the chain rule. With the product rule, we're going to be using u and v. So if we start out with a function that looks like a product of two factors. So in this case, the first of the factors is 2x plus 1, and then we have 3x plus 4. We use the product rule because these two brackets are multiplied by each other, so it's a product. So what's important here is that you look for the product of two terms only. You have to do a trickier method when you're working with 3 or 4 terms. The approach to take with a question like this then is to let u equal the first of the terms, and as we did previously with the chain rule, we find the derivative. Derivative of u with respect to x is 2. That is to say, the derivative of that is 2. We also now have a second variable that is for the second of the terms. In this case, it's 3x plus 4. The derivative of that is going to be the derivative of v, because the function is called v, the derivative of v dx, and that will be 3. The way we go forward is all 4 of these are going to be necessary, because the rule that I'm going to use is dy dx equals u times dv dx plus v times du dx. You may notice that in each case here, the u and the v are opposites. Okay, so one gets combined with the other's derivative. To complete the question, we substitute u dv dx, v du dx into our rule. So we're going to get dy dx equals, now the first we mentioned is u over here on the left, so that is that. So we put a 2x plus 1 there, but we're going to multiply that by dv dx, which is here, times 3. Then we're going to add to that the v term, which is 3x plus 4, multiply that by du dx, which is this one here, which is 2. So you'll see in the final version of your working, you should have each of the terms used exactly once. That is, the 4 terms that are merged in your working, u du dx and v dv dx, get used exactly once. On the next page, I'll just show you how we finish the question off. So continuing our question from the previous page, we had the working that was incomplete was dy dx, and then we had u dv dx plus v du dx. And remember, these are opposites, u and v and u. The working then that we had was that the first u term, okay, was 2x plus 1, and then we had, that was times by 3, then we had a 3x plus 1, which was the v term, and then finally the du dx term, which was 2. And those 4 terms in this line of working here describe the 4 parts of the preceding, the u, the dv dx, and the v du dx. Those 4 get put in. In a question like this now, the work really is to simplify this down. You can see that we're dealing with just a single set of brackets. It's relatively straightforward. That's going to be 6x plus 3, sorting this thing out, plus 6x plus 2. We'll get 12x plus 5. Okay, so the derivative is 12x plus 5. It's worth noting that had we gone back to our original function, which was y equals 2x plus 1 times 3x plus 1, had we crab clawed or foiled this out, you would have got 6x squared plus 5x plus 1. If you take the derivative of that, you would get 12x plus 5. That is to say, the derivative of that is 12x, and that is 5, and that is 0. So what's important to note is we've done and shown that the product rule gives us a correct answer. Why would we bother using the product rule then? If your original u and v functions are either so big as polynomials that you don't want to crab claw the whole thing out, or it's possible, and this is going to be leading to some year 12 work, each of those products, or the 2 terms of the products, won't be polynomials. They could be exponential terms, they could be trigonometric terms, and the algebraic method of expansion doesn't actually get you what you need. So that's one example of the product rule. I'll do a couple more in a moment.